to our channel. Today we'll be talking about acid and bases. It's O-level chemistry. This is a chapter number 7, and in this chapter it's a very long chapter, technically speaking. So we have 7.1 deals with the basic properties of acid and bases, and 7.2 talks about the basic oxides, the empiric oxides, the acidic oxides. And the last section, 7.3, deals with the salt preparation and that stuff. So in this particular video, we'll be discussing only 7.1, which is the basic properties of acid and bases. And in further videos, we'll be looking on into 7.2 and 7.3 as well. So starting off with acid. Now what is acid? Because one states that the aqueous solution of acid contains H+ ions and aqueous solution of alkalis contain OH ions. So okay, now what does this mean? Acid is a substance that produces H+ ions in aqueous solution. So acid, okay, I forgot the I, produces H+ ions in aqueous solution. Now we have types of acids. We have mineral acid, and then we have organic acids. Organic is a class of compounds. Again, organic refers to any compound that has carbon in its formula, and organic acid refers to any compound that has COOH in its compound. So for instance, the example that it's also included in our syllabus is ethanoic acid. Ethanoic acid is also known as vinegar in normal terms. Ethanoic acid has a formula of CH3 COOH. So it's a compound with 2 carbon in it. This is all for the introduction of acids. Apart from this, so we looked at the example of organic acid, which is ethanoic acid, the most common one. Now we'll be looking at the mineral acids. Mineral acids again are very popular class of acids. These include one of the most strongest acid known, HCl. They include H2SO4, which is sulfuric acid. They also include phosphoric acid, which is H3PO4, and lastly they also include again a common one, nitric acid, HNO3. Now these 4 are a few examples of mineral acids: hydrochloric acid, sulfuric acid, phosphoric acid, and nitric acid. These acids can be classified into monobasic, dibasic, or tribasic, depending on how many moles of hydrogen they give out in aqueous solution. For instance, let's take HCl, never mind. HCl will only give 1 mole of hydrogen. Therefore, it's known as a monobasic acid. It's monobasic. Now we have nitric acid as well. Nitric acid again gives only 1 H in aqueous solution. So we have H+, and we have NO3 negative. So it's also a monobasic acid. So looking at dibasic acid, we have sulfuric acid. Sulfuric acid is a dibasic acid because in aqueous solution it gives 2 moles of hydrogen ions, and that's why it's classified into dibasic acid. And followed by this, we have our tribasic acid, phosphoric acid. Phosphoric acid is H3PO4. So in aqueous solution, it would give out 3 moles of hydrogen ions, and obviously a phosphoric ion as well. So that's our tribasic acid. So before we move on to the properties of acids, I would like to first tell you about what strong acid and weak acids are. Strong acids, they completely ionize in aqueous solution, and examples are HCl. Basically all the mineral acid examples I mentioned over here, like HCl, phosphoric, sulfuric, and nitric, these all four are pretty famous examples of strong acids. And weak acid is something that partially ionizes in aqueous solution. So for example, we have ethanoic acid, CH3COOH, which is an example of weak acid, and it partially ionizes in aqueous solution. So definitions would be: strong acid completely ionizes, and weak acid would be partially ionizes. Furthermore, because if you know what acidity and basicity means, acidity is what value a compound has on a pH scale. Now in pH scale we have values from 1 to 14, right? So let me just give you a brief overview of what pH scales are. Scale is basically a value that is assigned to a compound that when dissolved in water. So for instance, I have a compound, it dissolves in water and it gives me a pH value of 2. Now 2 lies between we have 1, we have 7, and we have 14. So 2 lies somewhere over here, right? And because 2 is very close to 1 and it's very far away from 7, so it means that the compound is very acidic. So from this we infer that all the compounds that have a value of 1 to 7 are acidic, and those compounds that have a value of 7, from 7 to 14 onwards, till 14, are basic, and those that have a value of 7 in aqueous solution are taken to be neutral. So we've discussed the pH scale, so this is side knowledge for those who didn't know about what pH scales are. Moving onwards, strong acid is something that gives a very acidic pH in aqueous solution. So it means that its pH would be either 1 or either 2. For instance, HCl has a pH value of 1.4. H2SO4, I don't know what the exact pH value is, but I'm sure it's somewhere between 2 and 1 again, which is a very strong acid. However, on the other hand, so they have very low pH value. On the other hand, weak acids, they have comparatively higher values of pH, like 6 or 5 or 6.5, but they are less acidic. Obviously, they are weak acids, so they would be less acidic. Now we'll be discussing the properties of acid. Properties of acid are very, again, simple, straightforward, and easy. Properties. Okay. I like to use different colors because I don't know. That's just me. Properties of acid. Now, acidic properties. These are very important points. They can be asked in theory section for 2 to 3 marks, or even in MCQs. So properties of acid includes they turn litmus paper red. Litmus paper is a universal indicator. It's like a way of checking out what of a compound, if it's acidic or basic. So for instance, acid turns litmus paper red. basic compounds, however, on the other hand, turn litmus paper blue. So if a compound that's turning litmus paper red is turning red, that would be known as an acid. Furthermore, they are electrolytes, because now electrolytes are those compounds that can conduct electricity. To conduct electricity, we either need ions or we either need free electrons. They are So yes, as I was mentioning, that to conduct electricity, we either need ions or we either need free electrons. Now these compounds, if you see, they are being ionized, which means they are giving out ions. So these ions are the ones that can conduct electricity. Therefore, they are classified into electrolytes. And some of the properties also include reactions of acid with salts, with metals, with bases, or with carbonates. So we'll be looking on each of these reactions one by one. First and foremost, acid. I don't know why I'm forgetting the D always. Acid and metal give out salt plus hydrogen. So you have to remember this one line that I mentioned over here. Acid and metal always react to form salt and hydrogen gas. So for instance, let's take HCl, we take magnesium. This would react to form magnesium chloride and H2. And of course, we can balance out the equation as well. So that's one reaction of acid. Second reaction, we need 4 over here, is acid plus base form salt plus water. Now this reaction is known as neutralization reaction because it forms water. Now neutralization reactions are known for their equation that I'll be mentioning in a few seconds as well. But any reaction that involves an acid and a base, specifically a strong acid and a strong base, that reaction would be called as neutralization reaction. So let's suppose we take a strong acid, the good old HCl, we take NaOH. NaOH is also a very strong base. We will be discussing about base as well in the coming few minutes. So these two react to form NaCl salt and H2. Of course, we can balance out the equation as well. We have 2H, okay, we have 2Cl, and 2, and that's okay. Oh, it was already balanced. My bad. It was already balanced. My apologies. So yes, now neutralization reactions are known for their ionic equation. Now what ionic equation is? So now we have to talk about ionic equation, and discussing ionic equation and how to make ionic equation is a separate topic that needs to be looked into detail. So that brings me to another section of this, which is ionic equations. Now continuing this example above, we have HCl, it is aqueous. We have NaOH, it is again aqueous. They form NaCl, is a soluble salt, so again it is aqueous. And we have H2O. H2O is liquid. So now HCl is a very strong acid. It ionizes to give H positive ions, and I don't know most of them are writing these days. Okay, so it gives H plus, Cl negative, NaOH is a strong base and it gives Na ions and OH ions in aqueous solution. And NaCl again is a soluble salt, so soluble salt would give out its ions in aqueous solution. And H2O is liquid, so liquid cannot be H2O liquid cannot be ionized. Those compounds will be ionized which have aqueous written with them, or those salts that are soluble. Any gas, any solid, any liquid cannot be ionized, right? So we will be writing H2O as it is because it is not ionized. Now all these compounds that I mentioned, H positive Cl, NaOH, all these are in aqueous state. Now if you look closely, let me use this another color. So we have Na positive over here as well in aqueous state. We have Na positive over here as well in aqueous state. We have Cl over here as well in aqueous state. We have Cl over here as well in aqueous state. So these ions are present in reactants as well and in products as well. So those elements or those ions or those compounds that are present in the same state, which is same, they have the same charge, like Na has 1 plus charge in the reactant as well as in the product as well, and it's an aqueous state as well in both reactant and product. So these ions are called spectators ions. Spectators ions are those that do not take part in the reaction because they haven't changed one bit. So spectator ions, let me just write down real quick that Na and Cl are spectator ions. Na and Cl, okay, Na positive and Cl are spectator ions because they did not take part in the reaction. Now spectator ions are to be cancelled directly because obviously they are not taking part in the reaction, so we don't need them. They are totally useless and therefore we will be cancelling them out. Cl will be cancelled from reactant and product both sides, and so would be Na. So we are only left with the ionic equation, and that's our H plus aqueous, we have OH negative aqueous, and then we have H2O liquid. Now this equation over here, this final equation is known as ionic equation. Now ionic equations are those equations that do not include spectator ions, right? So that's how you go about finding the ionic equation. Any reaction between a strong acid and a strong base would always come down to this final equation known as the ionic equation, right? And this equation is known as the neutralization equation because, as I mentioned above, any strong acid and strong base would give out this equation, and all the other elements like salt, like Na, like Cl, like SO4, or even in the case of phosphoric acid, PO4 3 negative would be cancelled out eventually because all four of these are strong acids, and if they're reacting with strong base, so they would come down to the function. Like for instance, if I were to give you another example, let's take NaOH strong base and H3PO4 strong acid. So they react to form NH3PO4 and H2O. So yes, I was talking about this equation, balancing this equation. So we have 4H over here, that's 4 over here, then we have 3 Na over here, so we'll be writing 3 over here. We have, let's see how many PO4, 1, okay, PO4 are balanced. I think that's enough for the balancing. We have a balanced equation. So quickly we will be writing down, okay, NaOH again aqueous, H3PO4 again aqueous. This is soluble salt, so we will be writing aqueous. H2O is liquid. So 3 Na ions plus 3 OH ions plus 3 H plus ions plus PO4. We have PNA over here plus PO4 over here, and obviously H2O as it is. Spectator ions are sodium. Cancel them out. Sodium, phosphate and phosphate cancelled. So we are left down with 3OH plus H2O. Okay, I think we had to write 3 over there or not. The 6. Oh, sorry. Over here, it's not 2, it's 3. Because 3H and 3H is 6, so that's 3 to 6. And then over here as well, it's 3H2O and 3H2O. So obviously we have 3 everywhere, so 3 will be cancelled out again, and we are left with OH plus H plus into H2O. Now this again, as you saw before as well, this is the equation of neutralization, the ionic equation of any strong acid, strong base reacting together. That's all for your ionic equations. Fifth property of acid is reaction of acid with carbonates. Acid plus carbonates if salt plus carbon dioxide plus water. Like for instance, we have HCl. Let's take Na2CO3 as a carbonate. Salt would be NaCl. We have CO2. We have H2O. Okay, so let's balance out the equation. 2 for 2 over here, then we have 2 over here. C is balanced, Cl is balanced, H is balanced, O is balanced as well. Right, that's amazing. So we write aqueous, soluble salt, Na2CO3, so aqueous, NaCl is a soluble again, aqueous, CO2 is a gas, H2O is a liquid. Now we will be breaking them into ions. Now remember, only aqueous compounds are ionized. No gases, no liquids, no solids. So 2H plus 2Cl plus 2Na plus CO2 negative plus 2Na plus 2Cl plus CO2 plus H2O. So as spectator ions, we have Cl, 2Cl and 2Cl. We have Na and Na. Spectator ions are cancelled, and we are left with our 2H plus, CO3 negative, CO2 and H2O. This is the final ionic equation of a reaction between an acid and a metal carbonate, which gives out salt, carbon dioxide and water. In all cases, like no matter what acid we're using, no matter what metal carbonate we're using, these 3 are the end products of this particular specific reaction. So now we will be going back to our CIA checklist to see what sections we have covered so far. We talked about, let's just use a pen to cut them. We talked about the first one, defined acid as proton donors and bases as proton acceptors, because now proton donors, proton is basically H positive, so we saw that acids are those that produces H plus ions in aqueous solution. So we dealt with two as well, stated that bases are oxides and hydroxides. Okay, we'll be talking about bases as well in a few minutes. We talked about 4, the reactions of acid. 5, we will have to deal with it in when we'll be discussing bases. 6 states neutralization, which means acid and base. We did this. 7 as well. Okay, so describe acid and alkalis in terms of their effects on litmus. Okay, so indicators we'll be talking about in the end after we're done talking about bases. 9 is done. So is 10. Okay, this 11 as well is done. Relative acidity and in terms of color and pH. Okay, so we are left with 3 and 5 for bases. Now 3 and 5 deal with bases, and 8 and the last point to 12 deals with the indicators that we'll be talking about in a few minutes after bases. Bases are proton acceptors. Like acids were proton donors, bases are proton acceptors. Now what does proton acceptor means is that they take up H positive ions. Now before diving into the definition, let's just first state what the definition is. Definition of base is that it's any substance that it basically includes all metal oxide and metal hydroxide. So a base can be divided into any substance that is either metal oxide or is either metal hydroxide. Now obviously not all metal oxides, not all metal hydroxides would be soluble. So those metal hydroxides which are soluble are known as alkali. So alkalis are, now what's alkali? Alkali are soluble metal hydro, like the famous example, the strong alkali Na with sodium hydroxide. Okay, so yes, I would like to add on some more points in the definition. So a base is a substance which reacts with acid to make salt and water. Let me just write down this real quick as well, because we don't forget this. Base is a substance that reacts with acid to form salt and water. And alkali is a substance which ionizes in water to give OH ions, because obviously it has an OH, just like NaOH has OH, so in aqueous solution it would give out its OH. And this OH, once in aqueous solution is ionized, it would take up the H positive from the acid and form water. So based on the definition we saw above, they say that bases take up protons. Now how do they take up protons? Like how are they proton acceptors? When in water, alkalis are ionized. Let's suppose we have NaOH. NaOH in water would form Na positive ions and OH negative ions. So these OH negative ions would then react with H positive ions from acid, and they would accept these protons and form water. So again, that's how we get the neutralization equation. Now a few examples of a strong acid and a strong alkali and a weak alkali are, just like how strong acids are completely ionized, a strong alkali would also be completely ionized in aqueous solution. For instance, NaOH, which is a strong alkali, it is completely ionized. Weak alkali, we have an example of ammonium hydroxide, NH4OH. This is a weak alkali. It doesn't completely ionize in aqueous solution, and it gives a reversible reaction to form OH and NH ammonium ions. NaOH on the other hand gives an irreversible reaction to form Na plus ions and OH ions. Another point to make note of is a strong alkali or a strong acid, they would normally or always give an irreversible reaction, that is that OH ions formed or H positive ions formed, they can't be joined together with the metal to form the alkali or the base again. Basically it goes in one direction only, the reaction moves in forward direction only. However, a weak acid or a weak alkali, they normally give reversible reaction, which means that reaction can move both in forward and backward directions. Therefore, we have less concentration of OH or H positive ions in aqueous solution. Properties of base. First, we have that it turns litmus paper blue. Second property is the reaction with acid, that base react with acid to form salt and water, as we already talked about earlier as well, so I'm not going to mention it again over here. Base react with alkalis. Okay, this is not base, this is alkali, because alkalis they react with acids to form salt and water. So please be specific in your paper as well, write alkali, not base. Alkali plus ammonium salts. It's U, not O, if you were wondering. Alkali and ammonium salts, they give out ammonia gas and obviously a salt and water. Now let's take a few examples of these reactions. For instance, we have alkali as NaOH. Ammonium salts, let's suppose we have a chloride salt, so it's NH4Cl. Now these will react to form a gas which is ammonia gas, and we have water obviously. Then the salt would be Na and Cl, so that's NaCl. You can balance out the equation, then you can again cancel the spectator ions. Like for instance, I already know that Na is a spectator ions, so Na will be crossed out. I'm just going to write it like Na would be gone because it's spectator ion. Then we have Cl will be cancelled out. This is a gas, it can't be ionized. This is a liquid, it can't be ionized. So we are left with OH ions plus NH4 plus ions. We have NH3 gas and we have H2O liquid. This is an ionic equation of a reaction between an alkali and an ammonium salt, which already gives out ammonia gas, which has a pungent smell, a very dirty smell, and salt and water. Apart from this, the third reaction is of precipitation reaction. Do we have precipitation reaction over here as well? Okay, no. We only have two reactions over here for this specific 7.1 section, and we covered both of them. Precipitation reactions are a part of salts and not this particular section for the matter. So we have done 5. We have done what? 3 we have done, because their bases are oxides or hydroxides of metals, and the alkalis are soluble bases or soluble hydroxides. Now we will be moving on to our final section. Let me just go real quick over some things that I'm not missing. The indicators, they basically tell you what pH value a compound has, or where does a compound lie on the pH scale. If it's a neutral compound, that would give a value of 7. If it's a basic compound, if it's a very strong base like NaOH, it will give a value of 13 to 14 somewhere. And if it's a strong acid like HCl, it will give a value of 1.4. So indicators are used for that matter to check what the value of pH is, or if a compound is acidic or basic. So let's start by making a table so that we can simplify the stuff for you all. We have indicator. Okay. And we have their color in acid and their color in base or alkali, whatever you want to say. It's better to say alkali, not base. And okay, I need to take those out. So first off, indicator is our litmus paper that we already covered. Litmus gives red in acid and blue in alkali. Second off, we have the universal indicator. Universal indicator is the most commonly used indicator. It's a mixture of different indicators, and it's one of the most commonly used indicator for the reason because it can tell you if acid is a very strong acid or very strong base or a weak acid, because normally, like for instance litmus paper, we can't know that if an acid is a weak or a strong one based on litmus paper, because obviously any acid, strong or weak, regardless of that, would give a red color. So if you want to know that if we know that this compound is an acid, now we want to know that what type of acid that is, like if it's a strong acid or if it's a weak acid. So for that matter, we will be using universal indicator because they have a different range of colors, and depending on the strength of your acid, those colors will be shown in aqueous solution. So universal indicator. Okay, now normally if it's like a strong acid, it would give a red color, and if it's like a strong alkali, then it would give a violet color. And even though it's sort of just labels, but I'm just going to tell you that universal indicator gives green color in neutral solutions. You don't have to remember it, but just for your general knowledge, I'm just throwing it out there. So third one is methyl orange. Methyl orange gives red color in acid, and it gives a green color it gives a yellow color in your alkali. So we have 3 red for now for acid, and we have like different reds of color for alkalis. So violet for universal indicator, yellow for your alkali, yellow for your methyl orange. And the last one is phenolphthalein. Phenolphthalein gives colorless in acid, and it gives a pink color in your alkali. So that's for the table of universal indicators of indicators and their colors in acid or alkali. Now moving on, I need to tell you one more thing which I believe is left. We've covered this as well. 8 is done. Now 12 states that describe how to compare hydrogen ion concentration, neutrality, relative acidity, and relative alkalinity in terms of color and pH using. Okay, so we have done this as well. The universal indicator, as I mentioned a few seconds ago, is one of the most commonly used indicator. And why is that? Because it's a range of colors. So for instance, if I were to tell you the range of colors of the universal indicator, we have red, then we have orange, we we have yellow, we have green. Where is yellow? We have green. Okay, we have green. Then we have blue and violet. Violet was for your alkali. Okay, right. Blue and violet. Now this is what a normal color chart of universal indicator would look like. Let's make a line as well, because why not? So we have from here to here. Now this red is for a very strong acid. Green is for your neutral, and violet is for your alkali. So any alkali that has a medium alkalinity, for instance, let's suppose it has a value of 11 or maybe 9, that's a very medium alkalinity. That would give a blue color universal indicator. And red and orange again, we don't have to know the exact values of what pH would give us orange or yellow, but yes, a very strong acid would give red color. An acid that has a value less than, for instance, an acid that has a value of more than 3 to 4, that would give orange, and an acid that has a value of somewhere between 5 to 6, that would give a value of yellow. So these are the color charts, and they were in the last pointer, they were actually talking to you about the relative acidity and alkalinity based on universal indicator paper results. Oh, okay, there's one more thing that's left that I wanted to tell you. It's general knowledge, and for those who don't know what salt is soluble, because obviously when you are asked to write ionic equations, so you need to know that if a salt is soluble or not, because if it's not soluble then it's will form precipitates, and salts that form precipitate are solid and they can't be ionized. So you need to know what salts can be ionized, which means what salts are soluble. So I will be giving you a rough chart as well to memorize, which will help you when solving practicals and theory questions. All nitrates are soluble, like sodium nitrate, potassium nitrate, magnesium nitrate, ammonium nitrate, or let's suppose we have iron nitrate. I don't think that's solvent. Okay, any metal nitrate is soluble, like literally all nitrates are soluble. So these are the best soluble salt you can pick if you want to make a solution. So all nitrates are soluble. All sulfates are also soluble, but we do have some exceptions, like for instance except barium sulfate, we have lead sulfate, and lastly we have calcium sulfate. These 3 salts are included in your syllabus, and these 3 salts or sulfates are insoluble: barium, lead and calcium. Now we have chlorides. Chlorides, again, all chlorides are soluble, except we have some exceptions like silver chloride, AgCl2, sorry, AgCl, Ag has a charge of 1, I'm sorry, AgCl, lead chloride, PbCl2, and lastly we have mercury chloride. Now these 3 salts are insoluble chlorides: silver, lead and mercury. And lastly we have carbonates. Now just like all nitrates were soluble, all carbonates are insoluble except some exceptions. all carbonates are insoluble except potassium, K2CO3. Okay, what's up with my writing? We have sodium and ammonium. Now, also potassium, sodium, and ammonium are few, like whatever salt you pick up or whatever salt you want to make with these compounds, they will always be soluble, like potassium nitrate, potassium sulfate, potassium chloride, potassium carbonate are all soluble. Similarly, sodium chloride, sodium nitrate, or sodium sulfate, or sodium phosphate, or sodium carbonate, again all are soluble. And so was the case with the last one, ammonia. And this is a chart that you need to remember. And thank you for watching.